Welcome, everyone. Thanks for being here for part 2 of this workshop about using applets to explore statistical concepts. My name's Alan Rossman, and I teach in the Department of Statistics at Cal Poly in San Luis Obispo, California, which is the same university, the same department as Beth Chance, who I'll introduce now. Beth has been at Cal Poly for many years and is an award-winning teacher of statistics. She's also spent a lot of time and effort over the past 25 years developing a collection of applets. Last week, we had part 1 of this workshop. If you missed it, there is a recording available, and I've probably sent you the link to the recording. If not, just email me and I'll respond with the link. But this is part 2 of the workshop, of course, and Beth will be presenting different applets that deal with different statistical topics today. So let me be quiet and turn it over to Beth.
Thank you. And I'm actually at home, so I'm not in the same place as Alan, but my internet seems a little slow today. So if I don't get to your chats right away, please be patient. Or if there's a lag, let me know. This is the topics that we wanted to talk about today. So the main thing will be about simulation-based inference. So what we mean by that and how we've implemented that in different applets, as well as what we do before we get to the applets. And then I think there's going to be some time at the end to talk a little bit about multivariable thinking. The link to the applets is the same. So if you go to that kind of plain link, this is the link actually with .com that's been around for a while. But then if you follow any of the links, or if you go straight to the 2021 applets, that'll be the new versions. And these are JavaScript applets, and they should work on Mac, PC, iPad, iPhone, etc. The main change with the 2021 applets is improving some of the accessibility, like screen reader and tabbing and things like that. I'll also admit I mostly test in Chrome, so if you ever find issues in a different browser, let me know. I maybe just haven't fixed it yet. So starting off with simulation-based inference. So what we mean by that is using simulation and randomization methods to help students understand the reasoning behind statistical inference. And we found starting with this, like very early in the course, can help students get that idea of inferential reasoning. And then you can build on that over and over again throughout the course. And you can both have them see how the simulation predicts the same types of results that what we'll call the theory-based approach predicts, or if the theory-based approach is not valid, now you have an alternative. You have something else that you can have the students do so they can still carry out their analysis, because it may be valid with smaller sample sizes when the theory-based approach is not. But we also find this does a lot of the GAZE recommendations as far as facilitating active learning, teaching students important concepts through visualizations and using real data, and so it has some benefits that way as well. So I'm going to try and start with this example that we sometimes call help or hinder. And that first link does get you to some videos that you can show to the students. I often have them look at these before they come to class to try and explain the background. So we're going to see if that works for us today. I don't know if you get sound. Oh, you even get sound maybe. And so you have this little object that's trying to go up this hill and tries a couple times and can't quite make it. But then this other object comes over, gives them a push. And we think that little dance of a jig up there is showing maybe happiness that I did make it to the top of the hill. And so what they do is they were showing these videos to infants, really young, pre-verbal, so 6 months, 10 months, 12 months sometimes. And they alternated that video and another one, which shows the same object trying to get up the same hill, and again, not being successful. But this time the second object pushes it back down. And so perhaps the infants will think that's a less happy outcome. And so then they'll present the infants with the two objects that that particular infant saw in their video. And then they see if the infant makes a choice that maybe they'd rather play with one of the objects rather than the other one. So there's a case where the infant made a clear choice. Here's another one where the infant makes a clear choice. So not all the infants made a choice, but the main thing I wanted to highlight is you'll notice the color and the shape of the objects changes. And so they tried to counterbalance that. So sometimes the infant is choosing a blue object to be choosing the helper toy, and sometimes it's yellow, sometimes it's a triangle versus a square, things like that. All right, so they just kind of show them these two videos until the infants kind of seem to be saying, yeah, I got it. Then they present them the two toys that they saw in their video, and they want to know if the infants seem to have a preference for the helper toy more than what we'll call the hinderer toy. So hopefully that's a little bit of enough background. The only sound in the video was just you could hear the thing bouncing up and down and rolling up and down the hill. It's not important. So as I say, they did several different versions of this study. One of them was 16 10-month-old infants, and 14 of the infants chose the helper toy. So are you completely convinced that this means infants did do some kind of social evaluation, even pre-verbal infants, and they seem to like this helping toy more than the hinderer toy? Or might there be another explanation? So maybe throw in the chat, what are some explanations for why so many of the infants chose the helper toy rather than the hinderer toy? So near the dominant hand, good. They did actually balance that as well, right? So sometimes the helper toy was on the right and sometimes it was on the left. Which one they saw first, they did alternate which one they saw first, and then they did show them both back and forth to try and maybe get rid of that first time effect. And maybe it was just random choice, right? Maybe there isn't really this social evaluation, and these researchers just got lucky, right? So there's lots of explanations. I'm going to narrow it down to two. I'm going to say one is that infants do choose randomly. There is no genuine preference. These researchers got lucky. And maybe the infants do have a genuine preference for the helper toy. All the other things that you're suggesting, right and left, color, shape, we're going to hope, and again, this was only 16, but we're going to hope that that got kind of balanced out and wouldn't explain why so many chose the helper toy, because it didn't seem to matter what color or shape they made it or which side they put it on or which one they showed them first. We're still getting a pretty strong majority here. So what we need to decide is whether that's enough of a majority to convince us that it couldn't have been random chance. So we're going to kind of start off with this, I'm not so impressed unless you can convince me that that wouldn't happen by random chance. And that's the core logic of statistical inference. How surprising is it to get a result like this by random chance alone if there was no genuine preference? Maybe we'll call that the null model, or hopefully I'll convince you you don't even have to be using any of that terminology yet. We're just trying to come up with some way of maybe refuting one more of these explanations. Can we refute or at least have convincing evidence against this random chance explanation? And I pose that to my students and I have them tell me, how could you decide if the students, I'm sorry, if each of these infants were randomly guessing, is 14 out of 16 surprising? And it doesn't take too long for at least one student to maybe think about flipping a coin. Can I flip a coin 16 times and get 14 heads? And they have some intuition about that. But I want to build on that intuition. I want to have them do it hands-on. So I will give each student a coin and ask them to flip it 16 times. So that's why we start with a small study. Have them count the number of heads and then come to the front of the board and everybody shares their results for the number of heads. We build up this distribution. Maybe we call it a null model. But again, or a null distribution, we really don't need that language yet, right? We just want to see where 14 is on that graph. And we want to decide if 14 or more could happen even with such a small sample size. And that's usually what the students will say, oh, 16, you can't do anything. Well, I'm going to tell you 14 out of 16. It does end up being pretty impressive. And so they end up getting an approximate p-value, but we've only done this in class, so maybe I only have 30, 40 dots on that board. So that's when I'll turn it over to an applet. But I do think it's important for them to have that first hands-on experience, even building that distribution, even being one of the dots in that distribution before we turn it to the technology. Because the technology will do it very quickly, but it'll also start to distract them, right? Because they're just going to be trying to break the technology is going to be their focus. So I'm going to go to the one proportion inference one. And when you start there, it keeps that coin tossing context. So we're going to start with probability of heads, and we're going to do exactly what you did when you were tossing the coins in class. We're going to toss a coin 16 times. We're going to see how many heads we get, how many tails we get, and then we're going to store that result for the number of heads down on this graph down here. And then we asked, did everybody in the class get the same result? We want them to kind of see that randomness. And then, or even have the same students do it more than once and see that they're going to get different results and there's going to be some randomness. And once they kind of trust the computer, maybe turn off the animation, maybe still do one at a time, but start building up that distribution and see, do they have some intuition for how often they should do this before they start to see a pattern here? But then maybe go 10 at a time or 100 at a time. And so we do like an applet that allows that to build up, where it stayed as individual dots for a while before it kind of morphed into more of a histogram, but we're still showing them that discrete nature. And I usually advocate at least 1,000 to think I've kind of seen that pattern, or have them look at the summary statistics and look at that pattern, see it's not changing so much. We have a pretty good idea. In fact, 8 out of 16, if it is a 50-50 process, makes some sense, and we could get that standard deviation as well. Of course, what we really care about is where's 14. And you might just want to start visually and say, I don't see a lot of 14s, right? So it's pretty hard to convince me that the researchers just got lucky and just happened to get 14 of guessing infants, getting it right, picking the helper toy 14 times. Maybe the next day you come back and say, well, let's do this thing called a p-value where we're actually going to count 14 or more. You may need to talk a little bit about why you do or more, but we have them do that and they look at the proportion of repetitions. And again, the technology makes that very quickly. We can add a lot more and see that that doesn't change very often. And so we're getting a sense of that long run relative frequency, how often 14 or more happens by chance alone. And that is a p-value, and they can now make conclusions based on that p-value. So they can say things like, it's pretty unlikely to get 14 or more heads if it was just a fair 50-50 coin. So that gives us strong evidence that these infants weren't just tossing coins in their heads, that maybe what the conclusion we'll draw is that there's evidence they have a genuine preference for that helper toy based on the videos that they were seeing, and they weren't just choosing at random. All right. I do think students get, well, let me do this first. If you want to follow up, this did vary a little bit. Not everybody got the same answer. I could repeat this thousands and thousands of times, and it still does change a little bit. So if I want everybody to get the same answer, there is a mathematical way that you could calculate all the different possible ways that these 16 coin tosses could go with this probability of 0.5. And that's the exact binomial distribution. So I do sometimes show that with them. So now you see the green lines are the perfectly symmetric binomial distribution. And we can compare these results and see that, my 6,000, 7,000 repetitions did a pretty good job of giving me that long run probability. You could also overlay a normal distribution and see how here's a case where that sample size is small enough that maybe that's not a great approximation. And I don't have to use the normal approximation. I could stick with the exact binomial, or I could stick with the simulation. And then students do seem to kind of get to this idea of it didn't really happen by chance alone. What I would follow up with is then maybe trying different values. So maybe even with the 14 out of 16, maybe I want to know whether 80% is a plausible value. I probably don't want to necessarily expect them to be right 100% of the time, but do I think 0.8 is a reasonable guess for that probability? When you do that switch, and I'm going to go back to just one repetition here, that does change the language that students see in the applet, and it changes the animation. So now we're not flipping a coin that's 50-50. We're doing this spinner that's 80% blue and 20% pink. And then we're going to count how many landed in the blue, and we're going to build our distribution that way. And again, that should be a good next step for students. They can build that distribution. They can start to tell you why that distribution centered at a different value than it was before. Or if I switch to proportion of successes, now it's centered at 0.8. And then we could still ask whether 14 out of 16 or 0.875 is unusual. In this case, we get a larger p-value. Again, we should expect it to match up pretty well with that exact binomial. And we could say we don't have evidence that 0.8 seems to be a plausible value. In fact, one reason I like this is then we could try another value. Well, is 0.9 plausible? So I haven't proven it's 0.8, it's 0.9. I'm telling you there's several plausible values that could happen here. And if you want to explore that idea further, you could use sliders, and that you can change that probability and it'll update that distribution and that kind of p-value. And you can kind of see, well, when do I start getting that empirical p-value below 0.05 and think that that's no longer a plausible value based on that observed result. And then especially when you have proportion of successes, you can increase the sample size and you can see how that distribution gets more symmetric and gets more closer together. And you can see approaching that normal approximation gets more reasonable. And then once students kind of understand this, or you get these big sample sizes, you can hide that information, and that just makes it a little bit easier to kind of take a screen capture. And then you have some other little options in there as well. But maybe that's a good enough overview on that. Right, so how do you translate from 14 to 14 or more for two? Well, if you want to do two-sided, yeah. So let me get rid of this and have a little bit prettier picture here. And let's maybe put in something that's going to be on there. All right, so there's my or more. You can toggle this button to do or less. You can actually do equals to as well if you want to kind of help them see that difference. But then for two-sided, we just have them check this box. And then it updates down here and updates the count here. And they can think about, oh, I need to look just as far on the other side. And then how you define what's as small a probability on the other side is something you can play with as well. But the traditional approach, especially if you have 0.5 and you have a perfectly symmetric distribution, would just be to go equally as far on the other side. All right. One thing we have tried to do more recently is give them a little bit of language, a little bit of a framework that we'll come back to many times when we are doing these simulation-based inference approaches. And so one is thinking about the choice of statistic, and I've already changed that on you. I looked at number of successes, I looked at proportion of heads, kind of thinking about what you're going to measure. And then what you're simulating is what could have happened under the null distribution and thinking about how to do that. So we've already done a couple simulations. We did the coin tossing and we did the spinners and thinking about why you need to change that simulation based on what you're assuming in the null model. And then thinking about that strength of evidence. And I even try to avoid saying, 0.05 or less. I think I did that earlier, but having them thinking about, the smaller that probability, the stronger the evidence against that null model. And we're never proving the null model true, but we're looking for these, believable values, the ones that don't have the small p-values. All right. So now I'm going to do that same strategy, but in a different scenario. And this is another one I like because you can get some videos and have students look at them online. But I will warn you that even now, or when I start talking about it or having students watch the videos, we all start yawning, right? And what this video is about is whether yawning in front of somebody makes them more likely to yawn themselves. And this video is nice because they went through several different experimental designs. But then they finally ended up with one where they went to a flea market and they had a trailer with 3 rooms. And so they would just take people out of the flea market and say, are you willing to participate? If so, walk with me to one of these 3 rooms. And so sometimes before they put them in that room, they would yawn in front of them, and sometimes they would not yawn in front of them. And so some people were given a yawn seed and some weren't. They analyzed their results. They found that they were 17% more likely to yawn when they had the yawn seed than when they didn't. And so the Mythbusters decided that there was little doubt that yawning was contagious. So I'm going to have you first look at these data. So the difference in proportions. And so this is how I'm introducing this statistic to students and having them practice calculating this statistic and making sure we all get the same result for that difference in proportions. And so I think it's starting to get a little harder to decide, okay, is that far away from 0 or not? We need to do a little bit more analysis to decide if we want to consider that a statistically significant difference, or however you want to call that. So again, I might start with the 2 possible explanations. So yawning is random. There's no connection with the yawn seed, right? They did randomly assign them to whether they got a yawn seed or not. So again, I'm going to cross off a bunch of other possible explanations and think that random assignment balanced everything out. And then we're going to see whether the yawn seed, or that the other explanation could be that the yawn seed really does count that. And so again, I'm going to start with a tactile simulation where I want to replicate the random assignment that was done in the study. So what we have students do is we give them 50 cards, like index cards, playing cards, whatever. But I need 50 cards. Once I have my set of 50 cards, I use it over and over again. We share it across instructors. We try and make sure we're not doing this exactly on the same day. The only requirement is we want to mark or somehow code 14 of the cards as successes and 36 as failures. So we're going to fix the successes, which are that the person yawned in this case, and the failures. That's not changing. So those people have those characteristics, whether they get yawned in front of or not. So we're going to fix those successes and failures. And that's how we're modeling the null hypothesis being true. Then we model the random assignment by shuffling them up, dealing out 34 and calling them the yawn seed group, and dealing out 16 and saying they didn't get a yawn seed. But we know there's no effect here. We know that doesn't change whether they're a success or a failure. So then we just get a new table and we're going to recalculate our statistic for that new table, and we're going to repeat that many times, and we're going to build a distribution, and we're going to see that observed result of 0.136. How surprising was that? And so where I'm going to cheat a little bit is I already loaded this into the two-way table applet, and I've chosen the generic 2x2 table. But then or check this box, and then I've entered in yawn seed and no yawn seed and yawn and no yawn. All right. So I'll tell you in a minute why I did this to you. But then I pressed use table. Here's my bar graph. Here's my 0.136. I checked my show table. Here's my observed two-way table. If you want to change which one's success or failure, you can. If you want to change the direction of subtraction, you can. Again, show people those options, show your students those options. And then here, my choice of statistic is the difference in proportions. So we've already done the tactile simulation. So I'm just going to try and give a little visual to convince them that the computer is doing exactly what they just did. So when I press shuffle, I'm sorry, let me go back here, get rid of that, went too far. When I press shuffle, all right, that's my mixing up, and they go back to two groups. I always have the 34 and 16 in those two groups. So if you watch this table, the margins stay fixed. All that happens is how that result gets distributed. Those four counts, that time it didn't change. All right, so we're just creating different tables where we know the number of successes and failures, and we know the group sizes. If you show them the data view, they're just seeing that the random variable, the response variable is changing. I'm just reassigning that back to that explanatory variable group. Or you can have them look at the plot and see that, yeah, I tend to get pretty similar looking groups. Every once in a while, I might randomly create a big difference in the groups, but random assignment generally makes those groups look similar. So again, you need to decide how many you want to do these. I do like starting with the little boxes. You can click on one to go back to the table. So what had to be true for me to get a proportion way out here? Here I could get negative proportions, positive proportions. In fact, they might start to guess that it's going to center around 0. Right, and again, sorry, I had the 0.136 in here already. So I'm going to count how often 0.136 or larger happens using exactly the same logic we did before. And in this case, I am going to fail to reject that null hypothesis. 0.136 does seem to be a difference. It's not a big difference. Random assignment alone does seem to, with some frequency, create a difference at least that big that we saw before. All right. And so again, choice of statistic, just change the simulation to match the random assignment in the study. We're still evaluating the strength of evidence. If you do want to change the statistic, you could look at relative risk. I might ask students to predict what that distribution is going to look like first, and then think about what they need to do differently now that they've gone to relative risk. So here the relative risk is 1.725, so I need to put that number in here. But you should see that that p-value is not changing, right? So let me go back to point. If I don't change the simulation, I just change the statistic, but I update everything to match, right? That is changing. Why is that changing? Did I enter a number in wrong? 1.725 might be better. I'm stuck. Oh, well, no, it's doing the same 13. It shouldn't change. right? Because there should, whatever you put in, as long as you match it, you should get the same result. All right. And you can even go all the way to just looking at the number of successes. You could go to chi-square. You can do lots of different things. All right. Let me actually go now to the yawning study because I've actually been lying a little bit. Oh, come on. So let me go to use data. Let me go to show table. 0.136. Oh, yeah. All right. There's different versions floating around. All right. So bottom line, we put in our 0.136, right? We're getting a not small p-value. The reason why there's different versions floating around and what I thought I could sneak in on you here is this is not the real data. I said consider this data, right? This is not the real data. The real data was actually worse in the sense that it was a 10-4 split. So it actually gives you an even bigger p-value, and you saw that a little bit with that p-value, more like 0.5. And that I do think can throw students off initially, because when they do kind of start here and they don't know what to put here, a lot of times they'll want to put 0. And so it's usually pretty easy for me to look around a room and see, oh, I got a big p-value. I'm seeing like half. They've probably put the number here. But if you actually use the right data for the Mythbuster study, this is the right p-value, and it's a little bit harder for you to know whether they're putting in the right information or not. Okay. So yeah, getting them to come back over here can be a little bit of an issue. And so you'll notice what we did is when they put in the wrong number here, we give them a little warning. So that should be enough to let them know you need to think again about what you need to put in here. And that warning should go away when we put in with the decimal point kind of the right number here. All right, because now the applet doesn't tell you what to do, and the applet doesn't just give you the p-value. The applet just gives you that warning that you're maybe not putting in the right thing here. Um, so that's definitely something to look out for. And part of the reason what you'll see as we do more of these applets, that the left-hand side, the left of this line, is always kind of the sample data. And then to the right of that line is your made-up data. And we've tried color coding this blue, right? So they don't put this number in either, that they always think about this as being, the shuffled data, not the observed data. But that's not enough. That's another common mistake, is they'll put this number over here as well. And the applet should let them know that that's a problem. Okay, maybe enough on that. Oh, I do have, actually, Todd, one of our collaborators, has done some really nice PowerPoint simulations. So if you want to use maybe more than 50 and you don't want to do the index cards, but you still want to give them that visual impression of that shuffling, it's actually, once you have it, you can change it. Now, I didn't change it. I cheated a little bit. I don't have as many over here as I should. But then you can show them a little animation, again, that shuffling and dealing and getting a new statistic. And that might be another cheap visual you can do, or in a larger class if you're not doing the hands-on simulation. All right. There is, if you follow the right link, meaning there's links that say with Fisher's exact test, then when you have your 2x2 table, so I'm just going to make up numbers now. Right? It'll also give you an option for an exact p-value. And again, I might not tell them anything about where this is coming from, but parallel to what they saw with binomial, when you have these simple proportions, it's easy to figure out exactly all the possible different tables that are there and how many of them have 11 or more successes in that top left cell, and they can get an exact p-value. And again, they can compare that to the simulation-based results. All right. So let me now go to a quantitative response variable. And again, I'll give you a little bit of background on this study. And partly because I like using this study because it gives students lessons about how important it is to get enough sleep. And so I give them some quotes from the article. I've been trying to give them, the covers of the article. This is real data. This is real science. In this particular one, they wanted to train people on what they call a visual discrimination task. So they're at a computer screen, they flash this screen in front of them, and then they mask it. And then they ask them questions about what they saw. And so in this case, they would ask, were these going horizontally or vertically? And was this like a T or a V? And so if you practice at this, you can get pretty good at it and you get faster at it, right? So then they just ask you those questions. And so what we're actually going to measure is your reaction time. And so they do a whole bunch of these, they practice on it. We're going to focus on reaction time. But then after the training session, that's when they introduce sleep deprivation. So one group was not allowed to sleep at all the night after the training. The other group was allowed to sleep as much as they wanted. And then both groups were allowed to sleep as much as they wanted at nights 2 and 3. So what they did is they said, we know if we test you the next day, keeping you up all night is going to impact your reaction time. That's not even an interesting research question anymore. Now the research question is these lingering effects. 2 nights, 3 days later, do we still see the sleep deprived group still performing more poorly than the control group? Right. I also like showing them this graph because I hate this graph. And so I can talk about why I hate, graphs that use all this ink to show me a mean and a standard error. But that's a talk for another day. All right. So they retested them, but they retested them and compared them to their original skill after the training session. So this is the only thing that's a little bit unfortunate about this example is what we're measuring are these improvement scores. So how much faster they were 3 days later. Did they learn from the task? Are they now improved, right? So we want positive numbers. So we are seeing more positive numbers for the group that was unrestricted sleep and a few negative or just less positive numbers for the group that was sleep deprived even 3 days later. So this takes a little bit of time to get the students used to what these positive and negative numbers mean. So I think there is some preliminary evidence that this group was doing better on average. The statistic I might choose to look at is the difference in the means. That turns out to be 15.92 milliseconds. And you might talk to them about, is that a practically significant difference as well? But I'm going to instead focus today on what are possible explanations for this difference. They were randomly assigned to these two groups. So it's possible the random assignment could create such a difference in the groups, or maybe there really is this lingering effect from the sleep deprivation. So actually, there's a lot of parallels here to what we just did with proportions. All I'm going to do differently, even in my tactile simulation, is instead of color coding the cards as success and failure, I'm going to write those 21 numbers on there. So students will recognize you need 21 cards to match the 21 subjects, and that you're going to shuffle them and deal them to a group of 11 and 10. So you need to keep track of which is which, and that we're going to recalculate the statistic each time. But what I'm holding fixed is that improvement score. So that's modeling null hypothesis being true. Doesn't matter where that card went, they're going to have that improvement score, whether they were sleep deprived or not. Again, we're going to build up a distribution and we're going to see how unusual our observed result was. So if you go to the two means applet, it does have this data preloaded in. Right, so here's our 15.92. Again, all my descriptive statistics and everything are on the left. And then if I show options, I do get a little visual if I look at the plot of pooling everybody together, redistributing them back out. Some that were in deprived group went back to the deprived group. That's the color coding, right? So we mix up which group they went in. Each time we do that, we're getting a different shuffled difference in the means, sometimes positive, sometimes negative, and we can build up a distribution, right? It's not going to be totally centered at 0, and this might bother some students. Hopefully it's kind of getting closer to 0 as you do more, right? But again, because of the discreteness and the unequal sample sizes, it's not going to perfectly balance out. So you need to help them decide, it's close enough to 0, right? And what you really care about here is that standard deviation, or back over here on the left, that 15.92. So where does that 15.92 fall? Are you doing a one-sided or are you doing a two-sided? Did you have that direction in mind to begin with? Again, I put in the right number so it didn't yell at me, and that's my estimate of the empirical p-value. Right. And then one thing that is nice here, you want to do something different? Let's do the difference in medians. Can you predict that's what's going to look like? All right, turns out it's not so bad here, but sometimes you'll see not such a mound-shaped symmetric distribution. You'll see a lot of clumping with the medians. Just remember you need to change this to match that. All right, then And now we're about halfway through the course. We'll be talking about t-statistics and thinking about how that follows a t-distribution. So if I put in the calculated t-statistic, then we can compare the simulation results to the theory-based results. And again, talk about which one you might trust with smaller sample sizes, but if it, when is the t procedure going to be valid, and so on. If you are going to the theory-based approach, you can come over here and get a traditional just confidence interval for the difference in means and so on. You can get an ANOVA table, all right? So you can get traditional output. The main thing is just now I like to ask them a lot, what does this number mean, right? This is now two-sided, right? So if I go to two-sided, it should match better, right? But I want them to be able to use that language with, oh, if I generated a whole bunch of these, how often would I get a result at least as extreme? Just describe this picture to me, and you're giving me a correct interpretation of a p-value, right? And so I really do assess that a lot on my students, not because I think it's the most important thing of the course, just I think they can get that logic. It's not that counterintuitive when they've gone through this process, right? This is all just in case everything broke. Here's what the difference in medians could sometimes look like. Not quite as pretty. And then, yeah, getting them to give me that interpretation and talk in terms of plausible explanations or not. All right. One more simulation while we're here, because it really ends up not being any different. The context here is the draft lottery. So you've probably seen this example. I won't go through it too much, but they were just pulling out birthdays of the year, days of the year, and assigning those to draft numbers. And so we want that to be completely random. We want any birthday to be just as likely to get a high or low draft number as any other birthday. And this is what the results actually turned out to be. So we've got the draft numbers that were assigned to different days of the year. And that looks random, but let's dig a little bit deeper. And so in the applets, I'm going to go to the analyzing two quantitative variables. So I'm going to treat these draft numbers and days of the years as both quantitative. And then in the pull down menu, I have draft lottery. So that should match. And we're going to keep draft number on the vertical here, right? And part of the reason we really like this one is because when you think about what you're doing here, and let me actually go to the data version, right? So all I'm doing, and I'm going to choose the correlation coefficient for now, is again, I'm just going to mix up which draft numbers go to which 1 through 366 days of the year because it was a leap year, right? This totally mimics exactly what they were hoping to do, right? There's no, are my infants really tossing coins kind of matching here? This is exactly what they were hoping to do. And this is what the correlation coefficients look like for what we believe is a perfectly random lottery. And so if we do thousands of these, and we look at what they got for their correlation coefficient, go ahead and do two-sided this time. So minus 0.226, right? I don't think what they saw happened by random chance alone. And so if you look at this more deeply, there's a little bit more here, there's a little bit more here, a little bit sparser here, a little bit sparser here. But this is a case where that might not happen, might not show up to an untrained eye, right? So now we can kind of back it up and say random lotteries don't give me a correlation coefficient that extreme by chance alone. So exactly that same logic. And it turns out, and there is a video for this as well. And if students watch it, there's a couple things happen. One is he keeps picking off the top, but the only reason that's a problem is they put all the Decembers in first, then all the Novembers, then so on, and they didn't mix it enough. So they were kind of ordered by month a little bit. And so then when they were just picking off the top, they did tend to pick certain months more often than others. I guess they did January 1st and then went up to December. So it kind of went down a little bit, right? So I see a little bit of a negative trend in here. All right. Any other simulation-based inference stuff I should say before we switch gears a little bit? Can you make scatter plots by month? And so here's one thing in the applets. What you would need to do is you would need a variable in here, all right, that was like month 1, month 2, month 3. So the applet recognized it as words rather than numbers. But as long as these are numbers, even if you did month one, month, just the numbers month, it's going to keep treating it as quantitative. If you did have a categorical variable in here, it will allow you to select it. But to be honest, it's not going to do, it's just going to do color coding, right? So you'd want to, sorry, gender maybe. You'd want to go to a different applet if you wanted to, switch these to box plots. So you could take it to like the comparing means applet or something like that. That'll give you the box plots. Right now, this one doesn't, it just color codes for the categorical variable. All right. So speaking of multiple variables, where I wanted to go next is this, and this is a newer applet. Sometimes they say under development, but hopefully this will work for us here. Called multiple variables. And it does have a little bit different setup where you just drag variables from this list to where you want them to be. So I could do like height, and then I could do foot size, and that'll give me that scatter plot. This is actually, if you're familiar with Plotly or R, it has some different features to it. And you can do a Plotly toolbar where now when I mouse over, I have some different options as far as screen captures and things like that. You can also give it a title, and you can edit these axis labels a little bit more easily. And so there's some different features to that. You can also do a little jittering. This, we'll see why that might be useful in a minute. So actually, I'm going to switch to what we call the FEV data set. So from the pull down menu and then use data. So while you're pulling that up, I'll explain FEV stands for forced expiratory volume. So we're going to think of that as a measure of lung health or just lung strength. So it's how strongly you can blow out air from your lungs in like that initial second. And so larger values indicate healthier lungs. And they collected data on this back in the 70s, seeing if there was going to be a connection with smoking status. So the first thing I want to do is compare smokers and non-smokers. All right, so I can drag FEV here. And it is good to stop and have students talk about this distribution. What do they mean? What's the standard deviation? What might be some sources of variability in these FEVs? But then I'm going to go smoker to subset, right? And that's what's going to split it up into those two groups. And I can add box plots to this. So this is what you might want to do if you just want to kind of do that exploration. And this does do box plots of different widths. So this was a much bigger group, a much bigger sample size than this one. So you can see that over here as well. And the color coding should link up. All right. You can also do an ANOVA table and a t-test here. And hopefully you're starting to scratch your head a little bit, because this is yes for smoker, had a mean FEV of 3.277. Non-smokers had a lower, right? These are the non-smokers, and they seem to have worse lung strength than the smokers. In fact, it's highly statistically significant. So we should be thinking about, why do our non-smokers have worse lungs than our smokers? And so again, just hopefully students will think about there's other variables, and these other variables might be related to both of these variables as well. So why we like this, I can just drag this back over, and now I could take age and put it in the explanatory, and I can see that there's a strong association between FEV and age as well. And so then I might want to see, does that relationship differ between smokers and non-smokers? So I'll put the smoker back in the subset by box, and I can separate this out if I want. I can add the regression equations, right? I'm not doing anything too fancy here other than just looking at these visuals and seeing that there is different behavior. And so putting that into context, and students are usually very good at being able to kind of explain what's going on here. And again, I went through very quickly with you and didn't allow you to think about this age variable. This age variable is 0 to 20, right? So there's not a lot of smokers from 0 to 7 at least, right? So I have a lot more non-smokers at all these different ages. And what is that slope telling me? That slope's telling me that the rate of increase, right? Your lung strength improves with age, but a much faster rate for the non-smokers than for the smokers. So we just want them to have some easy visual experiences with multiple variables, and thinking about how bringing in another variable can change those relationships that we were looking at. And so it turns out that smoking, how it really impacts your lung health is your lung development is not as good if you start smoking at an early age. But because we have this imbalance of who is a smoker and a non-smoker, that all the smokers tended to be older, it made it look like the smokers had higher lung capacity when we didn't adjust for age in that comparison. And I want to talk about this idea of adjusting a little bit more. And I'm going to switch data sets for that to this one called salary adjustments. And this is totally hypothetical data, although somewhat realistic. So we're going to look at salaries and we're going to compare what we called STEM and non-STEM faculty. All right. So as you might expect, the STEM faculty on average are making more than the non-STEM faculty in this data set. And I'm going to switch the display on you a little bit. I'm going to now drag this up here to make it more of a linear model. I want to kind of fit a regression line here. So I need to kind of code this numerically. I've only got two groups. I can fit a line between those two means. That's fine. But I'm going to code it numerically. And right now it's coding -1 for the non-STEM and 1 for the STEM. And so if I fit that equation, right, I'm just connecting those two means. If you go down here, you can change it so it does indicator coding instead, which just means 0 and 1. So then this means this is the average salary for the non-STEM. And this is what happens when I change from non-STEM to STEM, the average salary goes up that amount, right? So it doesn't matter how you code it, but we have this positive increase. We have this higher average among the STEM faculty. But there could be other differences between the non-STEM faculty and the STEM faculty. So for example, maybe more of the STEM faculty are tenured. So I want to add this to the model, and I'm going to add it above STEM in that explanatory box. So again, that's mostly just color coding, but it allows you to see, is there a difference in that breakdown between tenured and non-tenured, between the non-STEM and the STEM? And so we got a little bit of numbers here. This group is 56% non-tenured. This group is only 20% non-tenured. We also see that the blue tend to be higher than the red. So tenured do tend to make more on average, according to this picture, than the non-tenured. And so if I really want to make a comparison between non-STEM and STEM, I would like to get rid of this tenure effect. So one way to do that is I could find this difference between tenured and non-tenured. I could lower all the tenured that amount, and I could raise the non-tenured that amount. And that's going to put them on a more level playing field, right? And I'm going to do the same thing over here, but because this is close to 50-50, I'm going to have about as many moving down as I'm going to have moving up. But over here, a lot more of them are going to move down than going to move up. So hopefully you can see a little animation of that if I check this adjust values box. So these, the blue went down, the red went up, right? The blue went down, the red went up, but a lot more are moving down in the stem. So the purple line is my new connection between those means. So this mean didn't change too much because that graph was mostly 50-50. This mean lowered because that graph was mostly tenured. And when I subtracted out that bonus you get for getting tenure, that salary, right? Now I'm comparing people that have the same tenure status essentially. And so that should be maybe a more equal comparison in those salaries. This is not something I do with my intro stat students, other than just this idea of there are multiple variables and you want to take them into account. And that's why we can't jump to these cause and effect conclusions from these observational studies. And so you can do more playing around with that. Why we have this data set is I can change which one I'm conditioning on. I can change that distribution. So I'm going to change to tenured equal, right? And so now they're both 50-50. So what's going to happen when I do that adjustment? The moving up and the moving down is going to cancel each other out, right? I didn't have an association here, so it didn't make an impact. And then if I go to this tenured other, right? So now there's more red over here, right? There's more blue over here. So when I adjust, it actually creates a bigger difference between the groups, depending on what direction they're moving. So in my intermediate stat course, I do hope them to get get them to this type of reasoning along the way in the course. But mostly we just wanted to show you an applet that, the drag and drop is really nice. You've got some other check boxes where you can kind of look at those relationships two at a time to kind of see what's happening. And again, you have more traditional output down here if you want to focus on that with the students as well. All right, so I think that was what we thought we would get to. And again, a reminder of some important features, whatever technology you're using. Hopefully we've tried to model some of that. But if you have lots of questions, let us know. Oh, speaking of technology, this is another color coding. You can color code by a quantitative variable. But I wanted to give a shout out to JUMP, or just this idea of interconnected pictures. So in JUMP, I can make a histogram of, this is just horsepower, and I can make a scatter plot of acceleration by weight. And then if I check one of these boxes in the other graph, it highlights just the ones that had that horsepower. And so that's another way of saying, well, what's the relationship if I force the cars to have all the same horsepower? Let's go to a different horsepower and only look at cars with that horsepower, right? What's that relationship? And so this idea of, the subgrouping and the conditioning and getting students some nice visualizations of that. All right. So I'll pause here, and we will be sending out again a video as well as copies of the slides for both sessions. And then any questions we don't get today, we'll try and answer. We also will send out an invite for a Slack workspace. So part of this grant is to provide resources to faculty, and there's a discussion in that Slack workspace, a channel, I guess, that's just about applets and technology, if you wanted to join that and just continue the discussion that way. Alan's also going to be sending out an evaluation form about the workshops. We really appreciate your feedback on that. And then if we have a lot of questions we don't get to today, we were going to offer a virtual office hour next Friday at the same time. Alan will send out a link if you want to join that and have a little bit more one-on-one discussion, or after you've tried a few more of the applets. So Alan's also put a link to the evaluation form in the chat now as well.
Thanks very much, Beth. Please do fill out the evaluation form, everyone. That'll be helpful for two reasons. One, obviously, we'll use your feedback in conducting and planning future workshops. And secondly, this workshop is part of a project funded by the National Science Foundation. So we need, of course, to report back to NSF as to what we did and how well what we did was received. So we'd greatly appreciate your taking 5-10 minutes to fill out the evaluation form. I'm also going to put a link to the Slack invitation in the chat now. I'll also be sending these to you by email in case you just want to wait for the email. But if you're really eager, you can look at those things in the chat now. And like Beth said, she'll be conducting a virtual office hour next Friday, same time. I'll send you a Zoom link for that later.
And then Laura also posted in the chat another form where we're, especially for the Slack workspace and the professional development, what would you find most useful? What are you interested in talking more about or learning more about? And so that's another form if you'd be willing to fill that out as well. And then hopefully we can bring some more of those resources to you.
You want to address Rachel's question, Beth, which was, how can people find out what the variable names in the preloaded data sets are about?
The best thing would be to reach out to me. Most of the ones in here are in one of our textbooks. So if you had access to those, you could look at them, but not all of them. So for now, I would just reach out to me and with a specific data set, and I can give you more background information on it. Is that an okay answer?
Great,
Yeah, just the
you.
tenured other was a little like
that was all made up
other?
though.
Okay,
Yeah.
good.
Oh, yeah, and that was made up. So yeah, it would increase the difference between the groups. So you just had to make the association go the other way. Yeah. So that's a case where I did make up the data to make a specific point.
I'm not a good multitasker, but I think I just successfully sent you all an email message with the 3 things we've been talking about here. Later today, or maybe over the weekend or Monday morning, I'll send out another message with the link to the recording of this session, as well as the recording from last Friday. And I'll also get the final versions of the slides from Beth, and I'll attach those too. a later message. So sorry about sending you so many messages, but hopefully at least some of them are helpful to you. We do still have 4 minutes till the top of the hour.
And there's other applets if there's anything else you'd be interested in talking about.
We have
Or
4 minutes here if you have questions.
do you have an applet on this? And I'll give you a yes or a no. This is Natasha.
As you reflect on this workshop and also last Fridays, by all means, jot down your thoughts, either send them to Beth or come to next Friday's Q&A. Brett, you have your hand up. Go ahead, please.
Maybe a quick question. Has anybody used the applets and simulation-based inference in a truly online environment, asynchronous, successfully? And this is the longer part of the question. If so, how? You don't have to answer that right now necessarily.
The main thing is I do try and kind of make sure the instructions are side by side with the applet. And then they learn pretty quickly to make screen captures, and I do have them insert that for the assessments. So I've had pretty good luck using them there. You know, and just the fact that they're not having to download any separate software, it actually seems to work better than some of the other things in the online environment.
Here to join the Slack workspace. That's a great question to ask there, and you'll get I hope you'll get lots of responses from lots of people who have done that.
And I think there's a separate channel right now on online courses, or we can create one specifically for that too.
For those of you who have never used Slack, I'm still a novice Slack user, but I'm told that you don't need to download anything to accept the invitation I sent out. You can do it all online. I think it is more convenient if you become a regular Slack user to download the app, but you don't need to download anything to accept the invitation and check it out.
One thing, this is going to be a little too much of a plug, but since we already mentioned the textbooks, what I did during COVID, if you go to instructor resources, or not, somewhere, oh, first edition, lab activities. So this is what I gave them in the online, and these were all self-directed, right? They would just turn in these lab reports. So they come with Word files, and they're just answering questions in the Word file and then submitting that. And then sometimes we even break into breakout rooms, and they could work on labs with a partner, and you know, they were both screen sharing and things like that. You know, in Google Docs, you know, make it easy for them to collaborate as well. So if you want to talk more about that, let me know. And then you'll see that, yeah, these just embed all the applets in them.
I think it is the top of the hour, so I'm going to stop recording now in a moment. Thanks again to Beth. Thanks to all of you for coming. If you'd like to stick around on Zoom here for a few minutes, I think Beth has a few minutes, and I'll stick around also. But thanks again. Please do fill out the evaluation. Please watch for other emails from me and other members of the team here.